We now shift a bit the topic and come to an important analysis of the timescales and hence the temporal resolution that is needed in CFD-DEM simulations. The first important timescale we have already discussed. It is the contact time of a particle-particle collision. This timescale sets the temporal resolution needed for the DEM part of the solver. In case of coupled simulations, there are 3 additional flow timescales that need to be resolved. First, this is the particle relaxation time tau p, which we have already seen in the definition of the Stokes number. In the figure on the right, you see this timescale illustrated with a black continuous line for a very dilute and a moderately dense system. Please note that in the figure a slightly different definition of the particle relaxation time was used, such that Reynolds number effects are considered. This is why the curve changes its slope at approximately 100 micrometers particle size or 10 to the power of -4 meters. As you see, the particle relaxation time is typically not limiting. There is the blue dashed curve that is approximately 2 orders of magnitude lower. This blue line indicates the fluid relaxation time tau f, which is defined here on the left. As you can see, it is similar to the relaxation time discussed before, but is based on the fluid density and contains the particle volume fraction phi p. The figure on the right nicely illustrates the importance of phi p. The figure shows that the fluid relaxation time is small in dense systems because the fluid mass is small, but large in dilute flows. Clearly, tau f is the smallest and hence limiting timescale for particle sizes of up to approximately 200 micrometers. This brings us already to the final timescale, which is the current number-based timescale tau CO. That can be derived from the definition of the famous current number well known in the CFD community. The current number is typically limited to maximum unity, and this value has also been assumed to create the figure on the right. Note that U is here calculated from a freely sedimenting gas particle suspension with properties defined in the figure caption. Delta X is the grid resolution, which is approximately 2 times the particle size dp. Tau CO is the limiting time scale for larger particles, simply because the velocity scale u is becoming larger when increasing particle size. In summary, choosing adequate time step size in coupled simulations requires a careful thought about the involved physics. Last but not least, one must mention that additional physics may impose additional constraints on the time step size. For example, the heat relaxation timescale of the fluid may also be considered. Unfortunately, we don't have time to go into the corresponding details in this unit of the MOOC. As we now have seen how to choose an adequate time step, there is the question: what is an adequate grid size? And this brings us logically to the topic of an adequate spatial resolution. In the CFD field, this is typically done based on considerations on the smallest size of turbulent eddies that should be resolved. In addition to the single-phase turbulence considerations, note that such turbulent motion is induced mainly by fluid shear and hence often called shear-induced turbulence. In CFD-DEM coupled simulations, we also have to consider so-called cluster-induced turbulence, short CIT. Both SIT and CIT must be considered when picking an appropriate grid resolution. The reason is that CIT is caused by a fluid mechanical instability inherent to sedimenting gas particle suspensions. The resulting clusters have a characteristic size that depends on the particle's terminal settling velocity and the particle fruit number. They can have a size in the range of 1 millimeter or less. This is again illustrated in the figure here at the bottom left that we have shown already before. More data on the size of the cluster length scale is available in the excellent work by Sundaresan and co-workers that is cited here. Another important factor when picking a certain grid resolution are multiphysics aspects. Depending on the transported quantity, extremely high spatial gradients might be resolved. For example, when solving the radiation transport equation shown before, i.e. the P1 model equation, an extremely fine CFD mesh might be required. In case one combines the P1 model with a parcel-based approach as illustrated in panels B and C, this might lead to challenges as again illustrated here. The reason is that the required CFD grid size is then finer than the parcel size, and the mapping of particle information onto the CFD grid cannot be done with conventional methods. We will now progress to a chapter that provides details on such a special mapping operation, i.e. smoothing, that is necessary to allow such parcel-based simulations. But first, let us start with the basics of Lagrangian to Euler mapping algorithms. As illustrated here, particle information, indicated here in red, must be adequately mapped to the Euler fluid grid, indicated here in blue. In essence, this means that we have to reconstruct continuum properties from discrete, i.e. particle information. We have seen how to do this already earlier in our unit on post-processing. However, our limitation here is that the fluid grid size delta is typically only 1.5 to 3 particle diameters in size. This means that we have relatively poor statistics because in the worst case we have only a single particle in each fluid cell. Unfortunately, we have to live with such a poor statistical information. And in some special cases, the fluid grid size delta is even smaller than the particle diameter dp, as you have seen before. As you can imagine, some smart ideas are needed in these situations to get meaningful continuum properties. In order to achieve this, two strategies exist. The first one is a direct mapping to the CFD grid, which is often unstructured, i.e. it consists of a set of arbitrary polyeders. Such a mapping is performed, for example, in the open source tool CFD-DEM coupling, where mapping relies on a so-called divided scheme that uses sub-particle splitting and a subsequent smoothing algorithm that we will discuss later. Direct mapping is frequently used since it does not require additional memory, is easy to implement and works relatively well. Another strategy is to first use an intermediate mapping step to the DEM grid, e.g. the search grid that is often anyhow available in a DEM simulator. Subsequently, the information on this DEM grid is projected in an Euler-to-Euler interpolation to the CFD grid that again can be unstructured. For example, the XPS package available via insilicotrials.com XPS uses such a strategy for mapping. In essence, this strategy is similar to the direct mapping followed by a smoothing operation, since the first mapping to the DEM grid has a similar effect as smoothing. In what follows, we thus only focus on the direct mapping strategy with a subsequent smoothing step. As a side note, I would like to mention that the reverse operation, i.e. the continuum to discrete mapping or Euler to Lagrange interpolation, is straightforward and can be realized, for example, with trilinear interpolation. Next, let us talk about smoothness. As already mentioned, it is of key importance. For a clearer understanding, let us consider a one-dimensional space domain with the position coordinate x and the tick marks indicating the boundaries of the CFD cells. The red dot is obviously the particle, which is in between two cells, as you can see. The simplest mapping would be a point mapping, meaning that the full particle information would be transferred to the nearest center of the CFD cell. As illustrated in gray, this would be the CFD cell right of the particle. As you can imagine, this would be a totally non-smooth mapping and hence should be avoided. A more suitable strategy is lever rule-based mapping as indicated in blue. We distribute the particle information to a set of neighboring cells, with each cell getting a fraction that is proportional to the inverse of the cell to particle distance. Much better, but still not smooth enough. Therefore, literature has already quite early, as you see here below with the publication of Pirker et al., introduced the idea of diffusive smoothing, which is illustrated in green in this figure. What is done in smoothing is that the mapped quantities are redistributed in the surrounding cells, similar as in the physical process of diffusion, but with an infinitely fast diffusion rate and over a certain smoothing distance that the user has to specify. As shown in the recent review of Calderon et al., the quality of the resulting continuum property field, e.g. the porosity field, is much better in case of smoothing. In short, investing in such a smoothing operation is worth the effort. Let us now see what smoothing does in practice. Therefore, we have studied the so-called jet in crossflow configuration, in which a dense particle jet is injected vertically upwards into a crossflow flowing from left to right. Specifically, we have used a parcel-based CFD-DEM simulation using a relatively extreme coarse-graining ratio of 40, i.e. the parcel diameter was 40 times larger than the primary particle diameter. And we have used a relatively fine grid to capture the flow dynamics well. If we now look at the results with and without smoothing, see figure on the right and left respectively, we see huge differences. The simulation employing smoothing yields much better results, and the one without smoothing a quite unrealistic scenario in which there is essentially no dispersion of the injected particles. This illustration also concludes our discussion on mapping algorithms, and we can now start the final sprint in this chapter on how to couple the DEM and a CFD solver.